Hi, everyone. We're back in English. I was excited to be able to basically follow that talk, but my Spanish is nowhere near good enough to present in Spanish. I also taught this course in English. So anyway, my name is Rachel Kurchin. I'm junior faculty in the Materials Science Department at Carnegie Mellon University. And I taught the freshman first-year undergraduate Introductory Materials Science course this past spring. I'm a computational materials scientist, so there's no sort of computational prerequisites for the course, but I wanted to expose them a little bit to the power of computation to sort of help us understand things in material science. And I worked up a couple of demos, so this talk is just gonna show you a little bit of that, maybe teach you a tiny bit of material science, and also offer some of my own kind of reflections on how it went, what worked well, what was maybe a little more challenging, and what I hope would work even better in the future. Okay, so a little bit about the course. I already said a little bit about this. It's if you happen to know CMU course numbers, it's course number 27100. The title is Engineering the Materials of the Future, because we have to give them like fancy, flashy sounding names, but it's Introductory Material Science and Engineering. These courses are aimed at first-year undergraduates. So it's the introductory course. It's the course that's aimed at sort of tempting students into the major to like join our department for their undergraduate degree. And critically, there's no science or programming prerequisites. I happen to teach it in the spring, but it's the same courses offered in the fall, so they can be absolutely first semester. So we can't really presume any background knowledge of programming or anything like that. It's a survey course. It touches on a pretty wide variety of topics, materials classes, all of these sorts of things because the goal is to show them what materials science and engineering is about, get them excited about it, show them a little bit of everything. This, of course, presents some challenges because you can't really go deep into anything, right? I mean, the way I did it, I sort of chose to choose a few little snapshots to go a little bit deeper on, because I think it's important to get a taste of what a more deeper, detailed analysis of things looks like, but it's fundamentally a survey course. So the idea is to expose them to a lot of different things. The way that I organized it was themed around this thing called the materials tetrahedron. It used to be a triangle, and then they decided they had to make it in 3D. Professor Kurchin's hot take is that it should just be a triangle, because there's not that much difference between performance and properties, really. Performance is just kind of a particular weighted average of properties for your given application. But anyway, here's the materials tetrahedron. So this is really the core of materials science, is understanding these aspects and the relationships between them. So we have structure of materials at many, many length scales. So understanding structure down from the atomistic length scale all the way up to, a chunk of material that I can pick up and hold and throw against the wall. Properties, so things we can measure about a material. Its density, the way that it interacts with light or mechanical forces or anything like that. As I said, performance is really just how it performs in a given application. In my opinion, it shouldn't really be a separate thing. It's just kind of what properties are important for your given application. Processing, so how the way that we process a material can impact these other pieces, and then we often put characterization in the middle because that sort of ties it all together, how we actually, understanding how we measure these things, what we can measure, what's harder to measure, all of these pieces are really important. A really kind of foundational thing that often comes up in materials, it's most commonly introduced in the context of materials selection. So how do I choose a material for a given application, is this thing that's frequently called an Ashby plot. It's named after some guy named Ashby who came up with plotting things this way. And basically the idea is you can plot a bunch of different materials or materials classes. Oftentimes these are sort of logarithmically scaled axes, so it'll be two different properties. And the goal is to understand what's the sort of relationship between these properties. There's some sort of like Pareto type constraints that we can't really do better than a certain maybe ratio or some sort of relationship between these properties, and just sort of thinking about where we want to sit on that in selecting a material for an application. But there's also a lot we can learn about it in terms of understanding, why do these relationships exist? What about the structure, properties, processing relationships lead to these kinds of fundamental constraints? And then, of course, there are people who want to engineer new types of materials, fancy composites, this and that, to sort of move beyond these constraints. So the first little notebook demo I cooked up was, okay, this is going to be an interesting challenge because it's not mirroring my screen right now, but once I find the mouse, there it is. So basically I took, and this is a pretty small data set. I think there was like order of 100 or 200 materials. It was just one that I found that I could download that had a bunch of different properties defined, and cooked up this little thing. So basically the only thing I asked them to interact with, this was as an in-class activity, was to just sort of play around with these two dropdowns and sort of make their own plot. And then I had some stuff below that they could go and look and see, like, how did I actually pre-process the data and do all of these sorts of things. But really I didn't want them to have to interact with the code directly at all, and Pluto was a pretty great venue for that. So, okay, so we have density on the x-axis, let's put something else on the y-axis. We can try thermal conductivity. Okay, that's kind of interesting. Maybe specific heat, what happens there? Oh, that's kind of interesting. You see a sort of Pareto thing, and of course we get these nice little tooltips, and I set some colors by material as class. So we have, let's see, the gray was metals, the yellow ones are ceramics, the blue are polymers, and then I think the green were composites. Yeah, so we can see that not only do we see some relationships between these properties, but they're sort of clustering based on the sort of chemistry, the material as class. And basically, I just sort of set them loose on this for a little while and said, like, look at this, what do you notice? Do you want to like, oh, that's the same one, that's not that interesting. Can you sort of conjecture why these relationships might exist? And I'll note I did this on the second day of class. So they didn't really have any of the sort of formal vocabulary for any of this stuff yet. It was really just like, let's think about, based on what we know from, high school chemistry or whatever. Also, they can think about things like data. There are outliers in data, right? Like, does this material really have the high coefficient of thermal expansion? Like, I don't think so. So we can talk about like sort of messiness in data as well. It's a cool opportunity for a bunch of different kinds of things. So this was the first one. I'll go back to the slides now. And then the second one that I want to show you is related to crystal lattices. So this is a really, really foundational topic in material science and engineering, understanding how we characterize crystal structures in terms of how their symmetries, the shapes of the repeating units, the unit cells, all of these kinds of things. In distinction to a lot of the other early topics in this course, this is new to almost all of the students. Thank you. So a lot of other things that they learn in this class, they've seen a little bit of in a high school chemistry or physics class, and it's like sort of maybe seeing it in a little bit different light or framing it in a different way. This is a fundamentally different kind of topic. I'm running pretty short on time, so I'll go by this pretty quickly, but another piece is that 3D visualization is a really important skill here, and it can be a big challenge. So the other notebook I'll just show very, very briefly is meant to help them be able to sort of visualize crystal lattices as a function of the properties that or the sort of parameters of the unit cells. So we can change the lengths of the lattice vectors, we can change the angles with the nice little sort of Pluto draggy bits, and they can sort of drag around and see what this thing looks like, and it shows the primitive cell, and I made some buttons so that they could sort of snap to common standard crystal structures. All the stuff is on GitHub. I think I might have forgotten to put a link on the slides, but I'm Kurchin on GitHub. It's in there. It's called 27100 demos, so feel free to go take a look and play around with it. There's binder links. They take like a really long time to spin up, which gets me to my reflection slide with the little bit of time I have left. So I think Pluto is definitely a great way to expose students to the power of computation and sort of working and playing with data without them needing to actually write any code themselves. One thing I was worried about was like, would students have laptops, or would they forget to bring them to class, even though I reminded them the day before, or things like that. That wasn't an issue. Enough students, like more than half the students brought laptops and tablets so they could sort of do it themselves or sort of group around with a buddy, so that worked really well. The startup time of the binder thing was a big issue. I didn't want to have to make them install Julia on their machine, so I used this great thing that, I don't remember who it was now, if it was Fonz from Pluto or somebody else, hacked together a thing where you could actually run a Pluto notebook on binder, but this took like 6 to 7 minutes to spin up. And so I'm hoping that in the future, that's something that some of the Julia Hub tools around Pluto can address and make things smoother. That was really kind of the only downside that I ran into with this. I felt otherwise it worked well. I wish I'd had more time to make even more of these demos. And yeah, that's all I have. Thanks for listening, and I'd be happy to discuss more with anybody.